All right, hello IB Physics Year 1. Today we talked in class about how to derive constant acceleration equations from the graphs that we've been using to solve problems. So this is a quick video going over the same notes we did in class. If we have a graph of our velocity time, we can use that graph to help us calculate the acceleration. And the acceleration on the graph is the slope. Hey, we already know that. Awesome. Slope, which you already know, is the rise over the run. So that will be the change in velocity over the change in time. And IB likes to use these special variables for our initial velocity, which is u, which you can think of as the initial velocity. I like to think of it as the initial velocity because the letter u is kind of like a v with an I attached to it. It's not very helpful. This is how IB is. V means final velocity in IB, and so to calculate the acceleration or the slope, we'll take our final velocity minus our initial velocity divided by our time. This equation should probably seem fairly similar to what you've been doing on our problem sets already. And so we can rearrange that by multiplying t on both sides, so we get a times t, and adding u, the initial velocity, over to the other side. So our final velocity is equal to our initial velocity plus our acceleration times our time. So this is our first equation. It should go in the box on your equation sheet if it isn't already. We can do this same idea to find the displacement. We talked about in class that the displacement for a velocity time graph is the area under the curve. And so here this area we can think of as two different shapes, one triangle and one rectangle. So we need to find the area of both these shapes. To find the area of the rectangle, that will be the base times the height, and the area of a triangle, 1/2 base times height. And these actually have physics meaning. So our base for our rectangle is the time. The height for the rectangle is just that initial velocity. Our triangle's height, however, is a little bit different. The base is still the same, but the height we have to subtract the final velocity minus the initial velocity to get this total velocity. Then we can take this first equation that we got, that the final velocity is equal to u plus at. I can rearrange that to say v final minus v initial equals at. And I'm going to plug that right in here so that we have something that's not quite so complex as this. So that becomes at. And that means we have 1/2 times t times a times t. So that's t squared. So we get our second equation, and this equation helps us find s, which IB calls the displacement. I know, weird. I have no special trick for this one. Just remember, s means displacement. So our displacement is equal to the initial velocity times the time plus 1/2 acceleration times time squared. This squared, people forget all the time. Super important. Do not forget. But we can take this same graph and find the area under the curve in a whole nother way, because you happen to know algebraically or geometrically that this is a trapezoid. And you might say, I don't really remember how to find the area of a trapezoid. That's okay, I do. A trapezoid's area is its height multiplied by the two bases added together. So these longer sides are the bases. And so if we add these together, times it by the height, and multiply by 1/2, we'll get the area of a trapezoid. Physics-wise, this means we're going to take the initial velocity plus the final velocity and multiply them by the time, and multiply all of that by 1/2. So we have yet another really useful, important equation. This is equation number 3, our trapezoidal equation. And then we can get even another equation. And this one is a combination equation. We're going to do some algebra where we have two equations and we're going to combine them together to get rid of the variable time. Because sometimes you don't know the amount of time something happens for, but you maybe still want to know how fast it's going. And because we have these 3 different equations, we can combine 2 of them together to get rid of time entirely. So I'm going to rearrange our equation here into time is equal to v final minus v initial all over the acceleration a. And I'm going to take this and plug it in, just like we talked about in class, plug it into this variable t, so that the t gets replaced by all of this stuff. So it becomes this new equation. We've got t being replaced by v minus u over a. So then we're going to combine this together using some algebra. Have an algebra party. I'm a big fan of those. And again, I'm just rewriting it. Same thing. The 1/2 is just going in the denominator as a 2. And I'm going to simplify this. And so you might think it would be helpful to get rid of the fractioniness. So we're going to multiply both sides by 2a. And we get our new equation, 2s equals two things multiplied together. And oh hey, this probably looks pretty familiar to you from math class because it's a thing you can multiply together and FOIL. So you could pause the video and take some time to try this yourself, or you can just watch the video with me. We FOIL, we get a bunch of different terms. We can simplify our terms a little bit to make them look prettier, and notice something really important. There's u times v and negative v times u, which means those can go away. They add together to equal 0, and we get this handy-dandy equation that I'm going to actually simplify even further to solve it for just v squared, the final velocity squared, by adding our initial velocity over to both sides, rearranging and getting 2 times the acceleration times the displacement plus the initial velocity squared is equal to the final velocity squared. And so this equation is really handy because it doesn't have time in it at all. Super great. So anytime you don't know the time, this could be a really great equation to find either the acceleration or the displacement or the final velocity. Whew, lots of equations. So we have this big giant set of equations. They're really useful. We're going to be using them constantly because you might have noticed from our graphical problem solving that sometimes it's annoying to solve a problem graphically. Sometimes it's easier to use an equation. And so we have a bunch of equations that we can get from those graphs we made to actually help us solve these problems. The first equation that we found doesn't need the displacement. Means you can't find the displacement with it, but it's helpful to know what you don't need in each different equation. Because frequently when you're solving physics problems, you'll find out, oh, hey, I have everything except maybe 2 or 3 things. And so you want to know which equation is going to be helpful for you when solving that problem. The big important thing you need to remember, huge thing, is that you can only use these equations during a time when the acceleration is not changing magnitude or direction. So that means that the acceleration is constant. So our slope of our velocity time graph is constant. It's not changing. We don't have any of those funny steps going on. We can't use our equations when it's changing. Most of the time in IB Physics Year 1, you're going to find out that the acceleration is constant, and you'll be able to use these constant acceleration equations, which are really great. But later on in Year 2, you're going to run into some times when you can't use constant acceleration equations. And in fact, Year 2 students are currently learning about one of those things currently, which is pretty cool. You'll learn about it next year, don't worry. And then one last thing that I wanted to point out is that while we use our IB formulas in class, you'll also see these, and sometimes I'll forget and say the US style formula. You'll see these in college in the United States as slightly different formulas. In the US, we use the variable delta x, so change in displacement, instead of s. That's just how we say it in the US. Delta x can also be written as x final minus x initial, which is another thing you'll see in the US. And in the US, we use v final, and v initial is v with a little 0 next to it. They actually call it v naught sometimes. And so that's just a little difference that when you go to college in the US, you'll see. The handy thing about the IB formulas is that they're shorter to write because you don't have as many letters. And really switching between them once you become familiar with them is pretty easy. So hopefully this was helpful for you in either recapping the notes or getting them if you were absent, and have an excellent Thanksgiving.